Mostly, everyone uses Pinecone, Weaviate, or Milvus to build AI applications or AI systems. I was too, until I started wondering what was actually happening underneath. How are embeddings stored? How does similarity search work? What does retrieval fast at scale mean? Curiosity turned into a challenge, so instead of treating vector databases as a black box, I started to think, why cannot I build something of my own from scratch C++? But before that, we need to understand or know what databases actually are. So let's take a close look on it. At first, like many others, I thought vector databases was another database optimized for AI. Store some embeddings, run a query, get the result, simple. Or at least that's what I assumed. But the more I worked with AI applications, the more I realized I was relying on systems I didn't actually understand. Whenever a chatbot retrieved relevant information, whenever a pipeline found the right document, whenever a semantic search returned meaningful results, a vector database was quietly doing the heavy lifting behind the scenes. And yet, to me, it was still a black box. Started digging deeper. I learned the modern AI systems don't search the way traditional databases do. Traditional databases look for exact matches. AI systems search for meanings. When you type something like best laptop for coding, an AI model understands that it is quietly related to phrases like good programming computers or laptops for software development. Even though none of these words are exactly the same, the reason is embeddings. Every piece of text gets transformed into a vector, a point in high-dimensional space. And once everything becomes a vector, searching becomes a geometric problem. The goal is no longer finding matching words. The goal is finding the nearest vectors. That sounds simple, until you realize modern systems aren't searching through hundreds of vectors. They are searching through millions, sometimes billions. And suddenly, a new set of problems or questions appear. How do you store all these vectors efficiently? How do you search through them in milliseconds? How do you balance speed and accuracy? And how do production systems handle all of this at scale? That's when I stopped reading documentation and decided to build it myself. Now comes the fun part, actually building the database. I knew from the start that there wasn't going to be a simple solution for similarity search. Different approaches come with different trade-offs. Some are simple but slow. Others are incredibly fast but much more complex to implement. So I decided to experiment with multiple approaches and compare them against each other. Before implementing anything, I had to answer a fundamental question. How do you measure similarity between vectors? There are multiple ways to do this. L1 distance, also known as Manhattan distance, L2 distance, also known as Euclidean distance, and famously called cosine similarity is also here. L1 measures the total absolute difference between coordinates. L2 measures the straight line distance between points. And cosine similarity measures the angles between multiple vectors. Most modern embedding models are more about semantic directions than absolute magnitude. I decided to use cosine similarity as the primary metric throughout the project. Once the similarity matrix was decided, I started with the most straightforward approach, the brute force approach or brute force search. The idea was simple. Whenever a query arrives, compare it against every vector stored in the database. Calculate the cosine similarity or the cosine similarity score. Sort the results, return the top matches. No fancy indexing, no optimization, just raw comparison. The implementation was surprisingly small. A simple loop over all the vectors, a cosine similarity calculation, and a ranking step. And honestly, for smaller databases or data sets, it worked really well. The problem was scalability. If there are 100 vectors, that's fine. If there are 10,000 vectors or more than 10,000 vectors at once, every query suddenly becomes expensive. Every search requires checking every single vector in the database, which clearly wasn't going to scale. So I started looking for a better solution. KD tree. The next approach was KD tree. Instead of storing vectors in a flat structure, a tree recursively partitions the vector space. Each split divides the data along a specific dimension, creating a tree structure that allows large portions of search space to be ignored. Rather than checking every vector, the search algorithm only explores the region most likely to contain relevant results. This significantly reduced the number of comparisons required during retrieval, and for lower dimensional data, the performance improvements were quietly noticeable. But there was a catch. Modern embeddings often contain hundreds or even thousands of dimensions, and KD trees are known to struggle in very high dimensional data or data spaces. As dimensionality increases, the benefits started to disappear, which led me to approach used by many production-grade systems. HNSW, Hierarchical Navigable Small World Groups, or HNSW. At first, the name sounded intimidating, but the underlying idea is actually brilliant. Instead of organizing vectors in a tree, HNSW organizes them as a graph. Each vector becomes a node, and each node maintains connection to its nearest neighbors. The graph is built across multiple layers. The upper layer provides fast navigation, the lower level provides precise retrieval. When a query arrives, the search starts at the top layer and gradually navigates towards most relevant region of the graph. This all happens in a greedy way. The result is dramatically faster search while maintaining very high accuracy. Rather than comparing against each vector, the algorithm intelligently hops between nodes till it converges on the nearest candidate. All the components in this project, HNSW, was by far the most challenging to implement. At this point, I had three different retrieval methods: brute force, KT-tree, and HNSW. Now it was time to find out which one was actually performed best. I created a benchmark framework and started running experiments. Same datasets, same queries, multiple runs, comparing latency, comparing accuracy, comparing retrieval qualities, and that's when things started going wrong. The benchmark results didn't make sense. Some searches were returning completely unexpected rankings. Results that should have appeared at top were showing up lower in the list. At first, I assumed the implementation was wrong. Then I assumed the benchmark was broken. Then I started questioning every design decision I had made up to that point. Honestly, there was a moment when I was wondering why I had picked this project all at once. I could have been doing literally anything else. Instead, I was staring at logs and debugging vector search algorithms at 2 in the morning. After digging deeper, I finally found the problem. Actually, there were multiple problems. The first issue was inside my HNSW implementation. Some critical changes were needed in the graph traversal logic. The second issue was much more embarrassing. I was calculating cosine similarity correctly, but I was interpreting the result incorrectly. Cosine similarity rewards higher values. My ranking logic was treating them the opposite way, which meant I was effectively sorting some results in the wrong direction. So the retrieval system was doing exactly what I told it to do, just not what I intended it to do. And there was one more problem. The embedding I was initially testing with were custom generated vectors. They worked for development, but they weren't representative of real world semantic embeddings. As a result, even when the algorithms worked correctly, the retrieval quality wasn't always convincing. So I switched to real embeddings generated through Olama. Then I ran the benchmark again, this time using documents containing more than 100 sentences, and finally, everything started to click. The nearest neighbor's results made sense. The ranking looked correct. The filters behaved as expected. And for the first time, the system felt like a real vector database rather than a collection of disconnected algorithms. After weeks of building, debugging, benchmarking, and rewriting parts of the system, the results were finally on my side. And that's how I built my own vector database from scratch in C++. Now I need a new challenge, so here's the deal. Drop the craziest project idea you can think of it in the comments. The comment with the most like wins, and I will build it. Until next time, code, create, and conquer.